Large vision language models, LVLMs, are hindered by high memory demands of key-value (KV) caches, which renders conventional cache management strategies inadequate for multimodal instruction following models. To address this limitation, we propose elastic cache, a novel approach that applies distinct acceleration methods for instruction encoding and output generation stages. In elastic cache, importance-driven cache merging is employed to prune redundancy caches. This strategy identifies crucial key-value vectors as anchor points and merges surrounding less important caches with these anchors, thereby enhancing the preservation of contextual information in KV caches while allowing for an arbitrary acceleration ratio. For instruction encoding, cache importance is evaluated based on frequency, whereas for output generation, tokens are prioritized based on their distance with an offset, retaining both initial and most recent tokens. Experimental results on various LVLMs demonstrate that elastic cache boosts efficiency and outperforms existing pruning methods in language generation across multiple tasks. The significance of this research lies in the context of popular chatbots like ChatGPT, which leverage instruction following language models to handle diverse tasks based on input instructions. These models can integrate visual inputs, expanding their applications to multimodal chatbots, as seen in GPT-4v and LLAVA. By addressing the memory demands of these models, elastic cache enables efficient inference of vision instruction following models. In multimodal instruction following models, computational and memory demands pose a significant challenge, particularly in dialogue systems where real-time responsiveness is crucial for user experience. The quadratic computational demands of attention modules in transformers further complicate this task when generating lengthy outputs. To address these issues, the KV cache mechanism is employed in generative inference, storing and reusing key-value vectors for prompt and output tokens to reduce redundant computations. However, this space for time strategy often leads to substantial GPU memory usage, exceeding the memory required for model weights and limiting batch sizes and inference throughputs. Recent studies have explored pruning key-value vectors in the KV cache to reduce memory usage while maintaining language modeling performance. Techniques such as H2O and scissorhands utilize smaller KV caches and prune less important tokens based on attention scores when input sequences surpass the reduced cache size, enhancing both memory and computational efficiency. However, these methods have two main shortcomings. They only improve computational and storage efficiency when the sequence length exceeds the KV cache's maximum capacity, and their time-memory efficiency can be enhanced. The proposed elastic cache model aims to boost efficiency for any sequence length, independent of the cache size. It employs a cache merging strategy based on the importance scores of instruction tokens, complemented by a fixed-point elimination strategy in the output generation phase. This design yields significant inference acceleration while maintaining generation quality. The elastic cache model addresses the limitation of traditional KV cache mechanisms, where instruction encoding accounts for most of the theoretical computation cost, but the actual latency is negligible. This highlights that it's not just model weights but also the KV cache used in output generation that can become a significant bottleneck. The elastic cache technique introduces a novel parameter-free cache merging approach to preserve context in a compact key-value (KV) cache, enhancing efficiency for sequences of all lengths and maintaining multimodal instruction following ability. During instruction encoding, the method determines the importance of all key-value vectors and utilizes the most crucial ones as anchor points. Subsequently, it merges all key-value vectors in the entire instruction sequence with their nearest anchor point, adopting a layer-wise merging policy. This approach allows for an arbitrary acceleration ratio by controlling the proportion of anchors in the cache merging process. During output generation, the KV cache is dynamically managed by adding new and removing older key-value vectors as tokens are generated. The method employs a fixed-point elimination strategy at a tunable truncation point, balancing the cache between initial guidance and new content. This approach retains a length of initial vectors nearly equal to the input instruction length, better preserving context to follow instructions. Notably, the elastic cache method is completely training-free, requiring no additional fine-tuning, and can be applied plug and play to any multimodal instruction following model. This significantly saves the expenses associated with training extra-large models. The cache update strategy incurs only negligible computational overhead during inference. In experimental analysis, the elastic cache method was implemented in visual instruction following tasks, employing perplexity, PPL, and rouge as primary evaluation metrics to assess instruction following capabilities. The results demonstrate the elastic cache's ability to significantly accelerate processing speeds without compromising on the quality of instruction following or generating lengthy outputs. It consistently outperforms both distance-based and frequency-based cache management techniques, showcasing its potential for improving multimodal instruction following models. In multimodal instruction following models, inference efficiency and predictive accuracy are critical. To address this, a novel caching strategy called elastic cache is proposed, which dynamically adjusts the cache size based on the input sequence length. This approach enables faster processing and reduced memory usage, resulting in a 78% increase in actual speed compared to other cache strategies across various models and datasets. Recent language models, such as LLAVA, Mini-GPT-4, Multimodal GPT, and Instruct-Blip, have been designed to follow instructions containing visual signals by integrating visual representations into the input of large language models using linear projection or perceivers. In addition to enabling multimodal instruction following, model compression and KV cache management are essential for practical applications, with techniques like quantization, pruning, distillation, and offloading being explored. Unlike existing methods that focus on reducing the number of KV vectors stored in the cache, elastic cache accelerates sequences of any length while maintaining the capability to follow multimodal instructions and generate lengthy responses. This approach differs from GIST tokens, which require additional training, and streaming LLM, which focuses on processing long sequences. By dynamically adjusting the cache capacity limit, elastic cache achieves greater efficiency improvements, making it a promising solution for real-world scenarios where both time efficiency and performance are crucial. Elastic cache is a novel cache merging method designed for large vision language models, which play a crucial role in natural language processing by aligning with specific user intents and tasks. These models consist of two primary stages: instruction encoding and output generation. In the instruction encoding stage, the model receives and interprets system prompts, user-provided instructions, and chat history, which may include multimodal information. The instruction inputs are processed and encoded into a series of tokens, each transformed into key and value vectors that capture contextual nuances. These vectors are stored in the KV cache, providing the model with immediate access to contextual information for generating accurate responses. In the output generation stage, the model incrementally builds its response, token by token, referencing the KV cache to ensure contextual alignment with preceding tokens. This approach allows the model to maintain a coherent narrative or logical thread in its responses while staying true to the user's initial instructions. However, the operation of instruction following models is challenged by the high memory demands of their KV caches, which store all encoded tokens, key and value vectors. As interactions progress, the cache size grows linearly, significantly straining memory resources in complex or lengthy tasks. To address this, developing effective cache management strategies is crucial for balancing efficiency and accuracy in generating responses. The proposed importance-driven cache merging policy serves as the core proposal for cache management. This policy finds key, value vectors in the cache as anchor points to aggregate surrounding contextual information. The method addresses two primary questions: how to identify the most important tokens in the cache and how to merge the contextual information around these tokens. Effective cache management in key-value caches relies on accurately measuring the importance of key-value vectors. By leveraging statistical data and the stationary nature of statistical information throughout the inference process, future cache requirements can be forecasted. Analyzing past usage patterns within KV caches enables the development of policies that predict which vectors will be most pertinent in upcoming inference tasks, optimizing cache management and resource allocation. To identify the most crucial statistic for evaluating KV cache importance, An investigation was conducted, encompassing various statistics, including population types and statistical variables. The comparative analysis revealed that the layer-wise sum of attention scores yields the most effective performance. Conventional cache management strategies, such as cache eviction policies, discard less important vectors, overlooking potentially valuable information. In contrast, the proposed cache merging strategy merges surrounding less important cached vectors into a select anchor vector, determined by the importance of each token in the instruction sequence. This approach reduces the number of key-value vectors in the KV cache while preserving contextual information. In multimodal instruction-following models, the model operates differently in the instruction encoding and instruction following phases. Therefore, two policies are employed: cache merging for instruction encoding and cache eviction for instruction following. This distinction is crucial, as the instruction encoding phase requires preserving contextual information, whereas the instruction following phase prioritizes efficiency. In the context of the one sequence, two policies strategy, this section delves into the importance-driven cache merging policy for the instruction encoding stage. The model under consideration has L layers, each with K heads. For a specific token Xi, J, T in the JTH attention head of the ITH layer, its query, key, and value vectors are denoted as Chi, J, T, key, J, T, and V, J, T, respectively. The causal attention matrix A is a lower triangular matrix derived from these vectors, where N represents the attention score between the mth and nth tokens. The importance value of the nth token in the ITH layer is calculated as E, J, N equals PMAI, JM, N and then averaged across all attention heads in the same layer to obtain E, N equals 1, KPJE, J, N. This layer-wise pruning strategy allows for independent importance scores for each layer. A predefined retention ratio gamma is used to select the top Ni equals gamma T tokens, with indices Tk, K equals 1, 2, Ni, in ascending order. These tokens serve as anchor points for Ni buckets, defined by the bucket division equation, 2. For each attention head, the key value vectors corresponding to each bucket BK are averaged and stored in the KV cache, represented by equation 3. Each attention head has its own unique KVK, emphasizing the variability in cache storage across different heads. This policy facilitates efficient processing and storage during the instruction encoding stage, allowing for better utilization of the model's resources. Conventional caching strategies for large language models face limitations when generating new tokens. To address this, the elastic cache method is introduced, employing a queue-based system that systematically eliminates earlier cached vectors from a fixed truncation point upon adding a new token. This approach prioritizes initialized instruction guidance and closely related generation, while diminishing the significance of earlier generated content. Elastic cache is evaluated through extensive experiments on two prominent large vision language models, LLAVA 1.5 and QuenVL, demonstrating its effectiveness and efficiency in instruction following chat generation datasets. Two state-of-the-art baseline methods, heavy hitter Oracle and streaming LLM, are established for comparison, referred to as H2O and local, respectively. These techniques can be summarized as frequency cache and local cache. The elastic cache method ensures that the cache is dynamically adjusted, removing less relevant information and maintaining a fixed size. This approach is particularly effective in scenarios where the model is required to follow instructions and generate coherent responses. By prioritizing recent information and diminishing the importance of earlier generated content, the elastic cache method optimizes the caching process, leading to improved performance and efficiency. The experimental results demonstrate the superiority of the elastic cache method, outperforming the H2O and local baselines in terms of response quality and generation speed. The proposed method's effectiveness is attributed to its ability to adapt to changing input patterns, ensuring that the cache remains relevant and up-to-date. The elastic cache method has significant implications for the development of large language models, enabling more efficient and effective caching strategies that prioritize relevant information. The authors evaluate the elastic cache method on visual instruct following tasks, comparing it to baseline models such as LLAVA 1.5 of varying sizes and QuenVL7b. The results, presented in Figure 2, demonstrate the consistent outperformance of elastic cache on both perplexity, PPL, and Rouge metrics. The frequency cache method is discussed as a cache eviction strategy, which records the access frequency of each key-value pair in response to input instructions. When the cache reaches capacity, the least frequently accessed pairs are evicted to adhere to the predefined memory budget. The frequency counts are continuously updated throughout the generation process. In contrast, the local cache method employs a spatial heuristic for cache eviction, removing the most distant key-value pairs from the current prediction when the cache reaches capacity. The evaluation metrics used to assess performance are perplexity, PPL, and the Rouge score. PPL calculates the exponential value of the cross-entropy loss between the predicted and ground truth distributions, with lower values indicating better performance. The Rouge score, on the other hand, measures the quality of generated text by comparing it to the reference text, with higher values indicating better performance. These metrics are used to rigorously evaluate the performance of the elastic cache method on visual instruct following tasks, providing a comprehensive assessment of its effectiveness. The proposed elastic cache approach is evaluated using three distinct metrics: perplexity, Rouge score, and F1 score. These metrics capture various aspects of model performance, including uncertainty in predicting the next token and quality of text generation. Perplexity reflects the model's uncertainty, while Rouge score indicates the quality of generated text in terms of overlap with reference sequences. Experiments are conducted on two datasets: LLAVA description, a subset of 100 detailed description instructions from the LLAVA 1.5 training set, and MMVET, a dataset covering a diverse range of tasks to evaluate multimodal understanding and generation performance. To prevent data leakage, the instruction tuning period of the LLAVA 1.5 models is redone, and the 100 detailed description instructions are excluded from the evaluation. The elastic cache is implemented on three instruct tuning visual language models: LLAVA7b, 13b, and QuenVL7b. The first and most recent tokens are protected, and the recent distance during the generation period is fixed at 25 caches based on analysis results. The main results of the experiments focus on visual instruction following, utilizing the LLAVA dataset. The evaluation metrics employed are perplexity, PPL, and the F1 variant of the ROUGEL score. The proposed elastic cache demonstrates superior performance across both metrics compared to the baseline strategies, namely local cache and H2O cache, over a spectrum of KV cache budgets ranging from 1.0 to 0.2. Elastic cache outperforms H2O cache and local cache in terms of perplexity and ROUGEL F1 score on LLAVA description at a KV cache budget of 0.5. The dynamic pruning strategy of elastic cache effectively retains image-irrelevant knowledge, resulting in improvements of 4.34 in perplexity and 0.089 in ROUGEL F1 score compared to H2O cache, and 28.72 in perplexity and 0.165 in ROUGEL F1 score compared to local cache. In the win rate comparison using the GPT-4v API, elastic cache achieves a 38% win rate with a pruned ratio of 0.3, surpassing previous work by a large margin. The comparisons under GPT-4v evaluation demonstrate the superior robustness of the elastic cache mechanism as the pruned ratio grows. The inference speed of the novel elastic cache mechanism is evaluated within the LLAVA 1.5, 13b framework, showcasing practical efficiency. The evaluation is conducted under two distinct experimental configurations, with input sizes of 1024 and 624 prompt tokens, and generation sizes of 512 and 256 tokens, respectively. The results indicate that when pruning 80% of the KV cache, the elastic cache mechanism achieves a significant reduction in inference time while maintaining performance, as shown in Table 2. Overall, the elastic cache mechanism exhibits superior performance, robustness, and efficiency compared to existing methods, making it a promising approach for image question pair generation tasks. Evaluations of inference latency and throughput are presented in Table 2, where the KV cache budget is set to 0.2 on the LLAVA 1.5, 13B backbone. The results demonstrate that elastic cache achieves a maximum of 77.9% actual speedup and avoids out-of-memory issues in limiting cases, significantly improving batch model token latency and throughput compared to full cache. Ablation studies on the components of elastic cache are conducted in Table 3, with 4 experiments performed on the LLAVA 1.5, 13B backbone with a KV cache budget of 0.5. These experiments evaluate the key design of elastic cache using the perplexity (PPL) metric for the LLAVA detailed description dataset. The results show that fixing a specific discard position, employing emerging strategy, and applying a dynamic attention procedure contribute to better performance. Figures 3a, d present the ablation studies on discard position, merging strategy, attention procedure, and importance metric. The results reveal that fixing a specific discard position, using a cache merging strategy, and applying a dynamic attention procedure achieve better performance. Furthermore, the evaluation of importance metrics using moving average, mean, or sum shows that the sum importance metric yields the best performance. These ablation experiments demonstrate that elastic cache can achieve an actual speed acceleration of up to 78% compared to full cache baselines while reducing the memory footprint during inference. The experiments provide insights into the effects of each component in elastic cache, validating the design choices and highlighting the significance of each component in achieving improved performance. The performance of elastic cache in generating descriptions for image recognition tasks is a key focus of this research paper. In comparison to local and H2O cache pruning methods, elastic cache demonstrates superior efficiency and accuracy. 2 examples of image recognition questions are presented, along with their corresponding generated descriptions from each caching strategy. In both cases, elastic cache provides detailed and accurate descriptions, while local and H2O cache methods failed to generate rational results under the experimental settings with a key value, KV, cache budget of 0.5. The paper also explores the importance of calculating the importance metric of each cache based on the attention score. 3 simple strategies are examined: moving average, mean, and sum value of the attention score. The results show that summing up the attention score outperforms other methods to a large extent. Moreover, the authors analyze the robustness of their caching strategy in real-world text generation scenarios. They evaluate the performance under constrained conditions and observe that elastic cache demonstrates remarkable resilience in the face of these challenges. This suggests that the proposed caching strategy is effective in maintaining generationability even when resources are limited. These findings contribute to the overall understanding of the efficacy of elastic cache in enhancing the efficiency and accuracy of neural machine translation models. By providing a comprehensive comparison with other caching strategies and detailed analysis of its performance, the authors further establish the potential of their proposed method in addressing the challenges of caching in neural machine translation. The authors of the research paper delve into the impact of significant cache limitations on their proposed elastic cache approach, comparing its performance to existing baselines such as local and H2O strategies. Their findings indicate that when 50% of the KV cache is evicted, elastic cache maintains its ability to focus on image details and generate coherent, rational responses. In contrast, both the local and H2O strategies experience performance degradation under these conditions. Specifically, with a KV cache budget set to 0.5, the local strategy produces repetitive, looping text and fails to respond, while the H2O strategy yields significantly shorter responses. The authors also investigate the effectiveness of a fixed-point elimination strategy within the caching mechanism, aiming to determine the optimal position for fixation to enhance performance. As shown in Figure 3, experimental results suggest that anchoring the fixed point within the middle section of the cache sequence yields superior results, leading the authors to strategically fix the position at the 25 most recent caches. The authors conclude that their proposed elastic cache framework significantly improves the efficiency of inference processes in widely utilized instruction following models. This novel approach leverages an importance-driven cache merging strategy, utilizing attention scores as a measure of importance to optimize cache utilization. Experimental results demonstrate that elastic cache outperforms existing baselines, showcasing robust generation capabilities and remarkable speed improvements. However, the authors acknowledge some limitations of their approach, including the reliance on attention scores for cache optimization, which may not always align with the most computationally efficient caching strategy. Furthermore, they highlight a potential negative social impact, as the increased efficiency and speed of elastic cache might accelerate the deployment of AI systems in surveillance applications. The elastic cache model, a novel approach to compressing and accelerating large language models, LLMs, is presented in this paper. This technique utilizes activation-aware weight quantization to enhance efficiency in both computation and memory usage, making it more feasible for real-world applications. Building upon previous research in model compression techniques such as pruning, trained quantization, and Huffman coding, the elastic cache model introduces an innovative method called activation-aware weight quantization, AWQ. AWQ dynamically adjusts the precision of model weights based on their activation levels during inference, significantly reducing the memory footprint and computational requirements of LLMs without compromising their performance. The paper also discusses the importance of efficient evaluation metrics for summarization tasks, referencing the Rouge package for automatic evaluation of summaries. Furthermore, it highlights the significance of multimodal interactions between humans and AI models, as demonstrated by multimodal GPT. In conclusion, the elastic cache model offers a promising solution for deploying large language models in resource-constrained environments. By leveraging activation-aware weight quantization, this approach can potentially revolutionize the field of natural language processing and multimodal AI. Advancements in large language models have been a significant focus of recent research, with improvements aimed at enhancing efficiency, performance, and usability. One key area is instruction tuning, which has shown to greatly enhance model capabilities as demonstrated in Liu et al. 2023 and Liu et al. 2023. Visual instruction tuning also plays a crucial role, significantly improving model performance as seen in Liu et al. 2023. The concept of chain of thought reasoning is another important development, leveraging interactive reasoning to boost the capabilities of large vision language models, as presented in Liu et al. 2024. This method involves generating a sequence of reasoning steps to solve complex tasks, allowing the model to refine its understanding and generate more accurate responses. Structural pruning of large language models is another technique discussed, aimed at reducing computational requirements and memory usage without compromising performance, as explored in Ma et al. 2023. This approach is vital for deploying these models in real-world applications where computational resources are limited. Compressing prompts for large language models is also highlighted, reducing input size and improving efficiency, particularly useful for models requiring large input sequences, as demonstrated in Mu et al. 2023. Fine-tuning language models for specific tasks is emphasized, allowing the model to adapt to task nuances and improve performance, as discussed in Wei et al. 2021. Smooth quantization, a post-training quantization method, is mentioned, reducing the precision of model weights and activations without compromising performance, as presented in Xiao et al. 2023. This technique is essential for deploying large language models on devices with limited computational resources. Efficient streaming language models with attention sinks are also discussed, enabling these models to process input sequences incrementally and generate responses in real time, as proposed in Xiao et al. 2023. This approach is beneficial for applications requiring immediate responses, such as chatbots or virtual assistants. Lastly, the development of embodied vision language programmers from environmental feedback is mentioned, integrating language models with embodied agents that interact with their environment and receive feedback to improve their performance in vision language tasks, as described in Yang et al. 2023. These advancements are critical for deploying these models in real-world applications and enhancing their capabilities in various domains. In the elastic cache model, Two primary metrics are employed to evaluate the performance of the accelerated inference process: perplexity, PPL, and Rouge score. Perplexity, as a measure of predictive accuracy, quantifies the model's ability to forecast the next token in a sequence given the ground truth texts. This metric is critical for evaluating the immediate, token-level precision of the model, providing insight into its understanding of language structure on a granular level. The Rouge score, defined by Lin, 11, was used to evaluate the overall coherence and fidelity of the generated texts in comparison with the ground truth. The manuscript presents an evaluation of a proposed computational model's performance, focusing on two key metrics: perplexity, PPL, and Rouge score. Perplexity measures the model's predictive capabilities, with lower scores indicating better prediction. It is calculated as the exponential of the average negative logarithm of the predicted probabilities for each word in the text, given the sequence of preceding words. The Rouge score, specifically the ROUGEL score, assesses the similarity between the model-generated sentences and the target sentences. This metric is based on identifying the longest common subsequence, LCS, between the generated text and the reference text. The ROUGEL precision and recall are computed, reflecting the proportion of the LCS present in the model-generated output and the reference text, respectively. These insights are then synthesized into a single metric, the F1 score, which is calculated as the harmonic mean of precision and recall. Furthermore, the manuscript includes a PyTorch-style pseudocode representation of the proposed elastic cache mechanism, providing a clear, step-by-step guide to the algorithm's operational framework. This pseudocode is designed to mimic the syntactical and structural conventions familiar to users of the PyTorch library, ensuring that the logic and flow of the elastic cache are both accessible and immediately applicable to practitioners in the field. This facilitates the reproducibility of the results and enables other researchers to seamlessly integrate or build upon the caching strategy within their own computational models. Elastic cache, a novel caching algorithm, is presented in a PyTorch-like pseudocode. The algorithm takes as input past KV caches, the number of tokens, and attention scores. If the input KV cache is empty, the algorithm returns none. Otherwise, it computes the sequence length and generation length from the input KV cache and attention scores, respectively. The attention scores are then averaged along the first dimension. The algorithm calculates the sum of attention scores S for the sequence length if the generation length is greater than 1. The number of deletions del_num is determined as the difference between the sequence length and the product of the number of tokens and the ratio R. If del_num is less than or equal to 0, the original KV cache is returned. Otherwise, the algorithm updates the KV cache. The update process involves computing the fixed index fix_idx, iterating over the KV cache, and computing the keep_idx and throw_idx based on the sorted attention scores. The merge_idx is computed as the nearest index to the throw_idx in the keep_idx. The key and value tensors are then updated by gathering and scattering the indices, and the updated KV cache is appended to the KV_new list. If del_num is between 0 and 1, the algorithm updates the KV cache by concatenating the key and value tensors along the last dimension, excluding the fixed index fix_idx. The updated KV cache is then returned. This algorithm efficiently updates the KV cache using techniques such as mean pooling, sorting, and indexing, facilitating implementation in popular deep learning frameworks. The elastic cache framework is demonstrated through an interactive chat generation demonstration, showcasing its capabilities in powering a language model that engages in dialogue with users. The language model generates contextually relevant and diverse responses by leveraging the elastic cache to retrieve relevant information and produce coherent and informative outputs. A key component of this demonstration is the KV cache budget, set to 0.5, which controls the amount of information stored in the cache. This allows the language model to generate responses under a dialogue setting, highlighting the framework's effectiveness in supporting interactive and engaging conversations. The chat generation demo illustrates the language model's ability to produce meaningful and abundant outputs, with responses that are not only contextually relevant but also exhibit diversity in terms of content and style. This makes the conversation more natural and human-like. For instance, when asked to describe an image, the model produces a detailed and descriptive response, highlighting the serene and picturesque atmosphere of the scene. Similarly, when tasked with composing a travel blog post, the model generates a captivating and immersive narrative, emphasizing the unique features of the slanting tree and the surrounding landscape. The demonstration highlights the potential of the Elastic Cache framework to support a wide range of natural language processing applications, including chatbots, virtual assistants, and language translation systems. By leveraging the framework's ability to store and retrieve information efficiently, developers can build more sophisticated and human-like language models that can engage users in meaningful and productive conversations. The framework's capabilities can be further explored to enhance the performance and effectiveness of various NLP applications. The Elastic Cache strategy consistently outperforms local and H2O cache pruning methods in image text generation tasks, particularly when dealing with nuanced questions and limited cache budgets. Comparative analysis reveals that the Elastic Cache accurately answers user questions and provides detailed descriptions and explanations, whereas local and H2O cache pruning methods often fail to provide correct answers. For instance, when asked about the woman's mood in an image, the Elastic Cache generates responses that provide robust and nuanced descriptions, such as, "The woman is wearing a white tank top and shorts, and she is jumping on the beach. She is smiling and appears to be having a great time," and, "The woman in the image is captured and the photo is likely to be happy and excited. She is smiling and enjoying the moment." Tables 5, 6, and 7 evaluate the efficacy of each strategy under various key-value cache budget constraints, providing a comprehensive understanding of the capabilities and limitations of each strategy when the available cache is limited. Under a 0.2 cache budget, the Elastic Cache strategy correctly discerns the mood of the woman and provides a nuanced description, whereas the distance and frequency strategies struggle to deliver accurate responses. Furthermore, the tables demonstrate the limitations of the distance and frequency strategies in more complex scenes, where the model is tasked to describe an image. In contrast, the Elastic Cache strategy showcases its robustness in dealing with complex interpretive tasks, highlighting its potential in image text generation tasks. The Elastic Cache strategy is evaluated for its performance in image text generation under varying budget constraints, alongside two other methods, local and H2O. The comparison focuses on maintaining focus on key elements within images and generating coherent text outputs. Experimentally, the Elastic Cache strategy consistently outperforms its competitors in describing living room and baseball field scenarios across different budget levels. At a budget of 0.5, the Elastic Cache strategy accurately maintains focus on key elements, such as bookshelves, sofas, and chairs, whereas local and H2O methods exhibit text repetition and may even fail to answer questions. When the budget is reduced to 0.2, the Elastic Cache strategy continues to deliver accurate depictions of spatial relationships and interactions within the room and on the baseball field, demonstrating its adaptability and potential for handling complex scenarios. In contrast, the performance of local and H2O methods degrades significantly, leading to repetitive text generation. The experimental findings firmly establish the Elastic Cache strategy as the superior choice for image text generation in resource-limited conditions. This investigation contributes novel insights and methodologies to the domain of image text generation, highlighting the importance of the Elastic Cache strategy's high applicability and robustness for practical use. The Elastic Cache model, as demonstrated in Table 7, effectively identifies and describes the main focal points of an image with a lower budget, providing accurate responses regarding the relationships between individuals in the picture and making reasonable inferences about the context of a competition. An image depicting a baseball game in progress is analyzed, showcasing a batter holding a baseball bat, preparing to swing at an incoming pitch. The catcher and umpire are positioned behind him, ready to catch the ball if the batter misses. The scene captures the intensity and focus of a professional baseball game. The Elastic Cache model's output highlights the scene's key elements, such as the batter's action, the catcher and umpire's positions, and the crowd watching the game. This model outperforms other models, like KV cache and H2O, in terms of both accuracy and efficiency, particularly in resource-constrained environments. The results demonstrate the effectiveness of the elastic cache model in image text generation tasks, offering valuable insights for addressing challenges in such environments.